Good evening, everyone. My name is Amit. We have been discussing regarding problem solving regarding basic electronics course. We'll wait for a few minutes. Not many people have joined. In fact, only one. We'll wait for a few minutes and then we'll start. So, Sai Kiran, I request you to please wait, and we'll get started in a few minutes. All right, welcome again. Excuse me, welcome again. My name is Amit. I am a fourth year PhD scholar at Indian Institute of Science, Bengaluru, and I've been solving problems related to basic electronics course. That's NOC 23E62. This is our week 3, February 18. Let's get started. Just please confirm whether you are able to see my screen or not. The slides, that is. Are they visible?
Yes.
Okay. So
Yes, sir.
so in the previous two sessions we have talked about, in the session 1 we talked about Thevenin and Norton equivalence, and based on our ease we switched from Norton to Thevenin and vice versa, and then we solved a few problems regarding node analysis. That was primarily your KCL and KVL. Then we saw a few instances of where we use superposition theorem to arrive at the at the required voltages or currents. And finally we saw a bit of phasors are nothing but your how to express sinusoidal steady voltage or current in terms of the complex numbers. That's what phasor represented. And the session 2, that is the last session, we saw the transients, RC transient primarily, but a few problems on RL transients. RC is resistor capacitor, RL is resistor and inductor. And then finally we saw that how effectively, then we saw that how does switching impact the transient. So when you move the position of a switch, so how does the transient change, that is how does the current flow through a resistor, through a capacitor or an inductor change. And we saw a few examples. In this class what we'll be doing is that we'll be focusing on diode circuits. So that is for today's session. Right, so before doing that, let's have a quick look into what a diode actually is. I'll do that here itself. Just give me a second. Just hold on. I have a slide on it. Let me build it. Yeah, okay. Yeah. So you can, these are the physical diodes that you are that are available in the market, and this is how we have modeled them. So on the left, on the middle of your screen, you are seeing which is the ideal diode, that is when it's forward bias. So just to be more clear, a diode is I'm talking about junction diodes here. So here you have the P side and the N side, and this is the symbol, corresponding symbol for that. So by forward bias we mean if we connect the p side of the semiconductor to a higher voltage as compared to the n side, then this is the forward configuration. On the other hand, if the p side is connected to a lower voltage compared to n side, that is what we refer to as the um, the reverse bias. So in the middle you can see that this is the ideal diode, which means is that we are not concerned about any internal resistances and whatnot. We'll see that why we are not doing it. And then so this becomes a simple switch in forward bias. This means it can support any amount of current at, just as the, by the way, Vd is this voltage that we are talking about, the Vd, the voltage across the diode. So it can support any amount of current, right? And when it's reverse bias, that means when Vd is negative, then it will not support any current. So this means zero current, which means you can say it's a reverse bias. However, this is, since these are made of semiconductors, and the actual equation, that's, if you refer to Professor Patel's lecture, it is something like this: V over kT, and then there is a -1, right? Something like this. This is the expression for a current in a diode. So after, at a certain, so this is actually ideal diode's equation is an exponential function, right? It will rise something like this. So what we see is that since rise is very exponential here, so we just model it something like this. We just model this to something like this. By the way, the current is like this, not, yeah. So we model it to something like this, which is drawn over here. This is sometimes called as semi-real or a semi-ideal diode. So what's happening is that as soon as the voltage crosses 0.7 volts, right, the diode will start to conduct, and again we'll assume it can support an infinite amount of current. However, if the voltage across the p and diode is less than 0.7, we'll say that it's an open circuit and it will not be supporting any current whatsoever, and hence it can be drawn using this. So what we have done essentially is just we have added a battery to this circuit. That's what we have done, and this is the model that we'll be using throughout our discussion today. So just keep this in mind. I'll draw this again, the same diagram which was also referred to in the lectures, right? So now let's come to the first problem. So what we have, the question says, which of the following plot correctly describes V0 versus Vi relationship for the circuit shown in the figure. So you can see this is the output voltage that we are tapping from here, and the input waveform will be providing somewhat over. We don't know the nature of input waveform, so that's that, and we are required to find what is the nature of output waveform, right? So I'll try to do this, and now first what I'll try to do is just I have reproduced the circuit here, and this is the thing that we are required to find. Now what we'll do is that, so first of all, what diode model are we using? As I told you, we'll be using this diode model. So this is also referred to as V on. So this is 0.7 volts. This is the current through the diode on the y-axis, and on the x-axis is the voltage that you are applying to the diode, right? So now let's just analyze this circuit, and what essentially is meaning is that in this region, that is just after V on, the diode is supposed to be on. So I'm writing this in words here: if Vd is greater than V on, diode D, let's name this diode D conducts. On the other hand, if Vd is less than V on, D does not conduct. Okay, so these are the two cases. Now what I'm going to do is let's take these cases one by one as to what's happening. So this is the case 1, and we have here case 2. So let's just first take the case 1. So that is when Vd is greater than V on. So I will do this analysis over here. So case 1, Vd greater than V on. By that I mean this voltage. This is the voltage that I am talking as Vd, the voltage across the diode. right? So if Vd is greater than V on, this means the diode conducts, and thus now the whole circuit can be replaced by this equivalent circuit. So rest of the circuit remains the same. Now only thing that will change is that now this will be replaced by a battery of 0.7 volts, right? And this is your Vi. This is how the circuit will look like, and the V out, obviously this is where we are getting our output from. Okay, so now we can clearly see now, so yeah, so now if you try to apply the KVL in this loop, okay, if you try to apply KVL in this loop, and let's say we are like going in this direction, this is 2 volts, right? And let's assume this current is I. So I can simply write Vi minus 1k times I, right, minus 2 minus 2k times I minus 0.7 equal to 0, and this will give me the value of I to be Vi minus 2.7 over 3k, and thus we can clearly see that V out, excuse me, and now from this we can obtain that V out is nothing but the voltage drop that you see over here, or you can calculate from here also, right? But I'm gonna do it from here. So that will be, so V out will be I times 2k plus 0.7, that is the voltage drop that is going to happen over on this leg, right? So that, so yeah, so this will come out to be, if I put the value of I over here, so that's coming out to be, if I put the value of I here, so it will be 2 by 3 Vi minus 2.7 plus 0.7, and if you solve it, so it will be 2 by 3 Vi, so it will be minus 0.9 minus 1.8, and then it will be minus 1.1. so that is the expression of V0 that we are getting. Okay, this is for the case 1, right? And let's say for case 2, so remember case 2 was what, when Vd was less than V on. So but how will the circuit look like? And we know that the diode will behave as if it's an open circuit. So I'll draw this circuit over here. So rest of the circuit will remain the same. That's 1k, 2 volts, 2k, and now this will be an open circuit, right? And this is the Vi that we are applying over here, and this is the V out. Now since no current is flowing, you can clearly see there'll be if I apply, you can say, then you can do the nodal analysis over here. So there's no current, no voltage dropping in this resistor, so I can clearly see that will be Vi minus 2 equal to V0, and if I rearrange, it will be V0 equal to Vi minus 2. Okay, so now I'm gonna rewrite this over here, that is for the case 1. So this was coming out to V0 equal to 2 by 3 Vi minus 1.1. so that was our first expression first, and this is the second one. This is the second expression that we have gotten. So I'll just copy these expressions, and now there's one more important thing, that what is the, at what voltage does this diode even turn on? You see there I have not put equality, so that equality condition is when the diode switches from non-conducting to conducting, or vice versa. So we'll also try to evaluate that voltage. So there are two ways of doing it. You can simply, what you can do is that since this is going to be there cannot be arbitrary jumps in assuming that they can the diode will turn on smoothly, right? Because you can see there's no discontinuity in current, right? So there are multiple ways of doing it, is that the current cannot jump abruptly in this resistor, right? So we'll try to do that, and alright, so let me just write these expressions over the next slide. So we got, for case 1 it was V0 equal to 2 by 3 Vi minus 1.1. this was the case 1, and second case we got V0 equal to Vi minus 2, right? But these are, so this is the on condition and this is the off condition, but we also need to figure out that when does this diode actually turn on. It's easy to see, as I told you that so when the diode is off, this is the condition. However, when the Vi starts to keep on rising, so what's going to happen is that this voltage will this out, the value of V out, right, will keep on rising. It will keep on rising, it will rise to such an extent the drop here becomes 0.7 and the current here is barely 0. So current will barely start to flow, because we remember that as I drew for ideal diode, right? So we are just operating here just below V on. This is ID versus VD. So this is the regime I'm talking about. The current is 0 over here just before that. So if I put I equal to 0, so I'll put V in when diode just turns on. So this is the voltage that we need, right? So how do we find that? We'll simply put ID equal to 0, right, in this circuit. So when we put ID equal to 0 and VD equal to 0.7 volts, because it's barely start to conduct, so VD is 0.7, right? So if we do that, so this is 0.7 and if this is 0, right, so I'll draw this circuit over here again. So this is 0.7, this is the complete circuit. So if you see, so there will be no current flowing, right? I'm saying it's just start to flow, so I can say I equal to 0, correspondingly I equal to 0 here also, right? So if that is the case, this means that if you see the V out in this, this is V out plus minus, so we can clearly say V out will come out to be 0.7 volts and thus V in will come out to be, you have to add 2 plus 0.7, so that will come out to be 2.7 volts. So this means this is the turn on voltage. This is the at this V in, the diode will start to turn on. So now we have everything, right? So now we have every information that we need. So this is the turn on voltage, 2.7 volts, and these are the two expressions. Okay, so we can, so let's just now try to plot whatever information that we have. So we know that for V in less than 2.7 volts, the expression should be V naught equal to Vi minus 2, right? So if you do that, this means it's a straight line with slope equal to 1. So for slope equal to 1, when V in is less than plus 2.7 volts. So when V in is plus less than 2.7 volts, let's say this is 2.7, right? So slope has to be positive. So this cannot be an option because the voltage has to be 2.7. So this option is ruled out. This option may be correct. This option is not correct because we know the slope has to be 1, right? So slope is 1 and let's again, this voltage is 2.7 volts. And finally, after that, the slope has to be 2 by 3. So after that, the slope has to be 2 by 3. So after this, the slope is not 2 by 3 here. So this option is eliminated. So we can see that D will be the correct option for this problem. So I'll summarize what I did is that I broke the problem into two cases. That is when diode is on and when diode is off. We derived the the V out versus V in for both the cases, which we can see as expressions 1 and 2, and then we identified that at what point does the diode turn on. That means what is the V in condition. So there is some V in condition over here. So what is that V in at which this switch happens? So we derived it to be 2.7 volts, and thus based on these three information, we plotted and we found D to be the correct option. So that's for problem 1. I'll pause a bit over here, and if you have any doubts, you can ask me. Otherwise, we can go ahead. So this is a diode related problem, but diode is a non-linear device, so you must be aware about it. Resistor is a linear device. When V is positive, so V equal to IR, that's how we see that. But diode, you saw, I wrote the expression diode, I versus V is an exponential relation. So but still we modeled our diode in terms of the known entities, that is our voltage source and switch. So just so as we can apply all the understanding of KVL and KCL even to an exponential and non-linear device like diode. All right, if there are No comments or doubts?
One question.
Yeah, please go ahead.
What is IS? IS exponential that you're writing here. What is IS?
Okay, let me go back over there. So where was it? Yeah, here, right? So this is what we refer to as the reverse saturation current. So if you see that there will be some current flowing. So let's say let's talk about some numbers. Okay, let's put this V to be negative, let's say minus 5 volts, and K is Boltzmann constant and T is your temperature. So this comes out to be around 26 millivolts at T equal to 300 Kelvin. So this quantity, when we put the number, this will come out to be exponential to the power minus 200. I'm talking about in this regime. Let's say V equal to minus 5 volts. So exponential raised to the minus 200 will be very close to 0. So we neglect this term and you get ID equal to minus IS. Okay. This means that when you reverse bias and a diode, there will be some current flowing. Remember that in our model we have assumed it's zero current flowing. That's not the case. The physics of diode does not allow zero current in reverse bias. It will allow so IS is usually very small, maybe in picoamps. Okay, which we have neglected for our model here, but it is some current is flowing, and since it's reverse direction and this current is not increasing, it's we assume that it has saturated. Note that it's coming out to a constant ID equal to IS. Hence this is known as reverse saturation current. I'll write this here. This is known as reverse. Why reverse? Because it flows, this is the current flowing when the diode is reverse biased. Saturation, because the current does not increase, actually it does increase, but not exponentially, it's a linear increase. Reverse saturation and current, and usually it's in the range of picoamps or in a few hundred of nanoamps maybe. So does that answer your question?
Yes, yes.
Okay, thank you. So now let's move forward and we'll come to problem number 2 now, right? So now this is the same problem, not same, similar problem as before, just that we have signed the polarity of this voltage source over here. So we'll again follow the same process. So this is the circuit that's been given to us, and again I'll redraw that the model that we are using this model. This is ID and this is VD, and again we'll assume that V on of 0.7 volts, right? Again I'll break it into two cases. So what I'll do is that first is my let's start from over here. That's case 1. That is we'll assume that VD is greater than, this is VD, the voltage across the diode, this is the diode D. We'll assume VD is greater than V on is 0.7 volts. Okay, so how will the circuit look like? I'll draw the circuit over here. So this is 1K, this is 2 volts, 2K. So we now know it will look like something like a battery, like this, right? And this is that, and this is the V out. Here we are applying a V in, and again I'll assume the current I is flowing through this circuit. And if I again write the KVL for this, so this will be VI minus I times 1K plus 2, because it's a negative polarity that we are encountering, minus I times 2K, and then minus 0.7. This is V on the same 0.7 equal to 0. This is 0.7, right? So if I solve this, I'll get I equal to, so this will be VI plus VI plus 1.3. 2 minus 0.7 is 1.3 over 1 plus 2K is 3K. So this is the current that I have obtained, and now I can simply say that V naught is nothing but, so if this voltage is 0, so we can clearly see that this voltage would be 0.7, and so if we apply Ohm's law across this, so this will be V naught equal to 0.7 plus, or you can apply KVL, however you may want to see it, I times 2K. So I times 2K, if I put it over here, so this will be 2 by 3 VI plus 1.3 plus 0.7, right? So if I try to solve it, this will be 2 by 3 VI plus, so this 2.6 by 3, that will be approximately 0.9. So plus 1, this is an approximate value, there will be not it will be slightly um, smaller than this actually. So 2.566 or something. I am rounding it off to, let's say, and this is the expression 1 for the case 1 that we had discussed. Right now let's do case 2. So case 2 is when Vd is less than V on. I'll again draw the circuit diagram. So now in this case, since the diode is turned off, this is a short 2K. This will be an open circuit, zero current according to our model. This is Vi and this is the V out that we have. So clearly no current is flowing over here. So if you write KVL in this loop, like in this leg, so we can simply say that Vi plus 2 equal to V naught, and thus that will give me V naught equal to Vi plus 2. This will be my second expression, right? Okay, so now let's populate this over the next slide. So V naught equal to 2 by 3 Vi plus 1.6, and then this is for on, and for off we got V naught equal to Vi plus 2. Now we can again eliminate some options. We can see that when it's off, again let's see, we have very small very negative voltage of Vi, let's say minus 10 volts. So what will happen is that this diode will not be turned on, this will be turned off, right, for very negative voltages of Vi. So what we can clearly see, for large negative voltage of Vi, there should be a slope of 1, right? So we can clearly see for large negative voltage, slope should be 1. So this cannot be an option. Again, this cannot be an option, and this cannot be an option. So we can clearly see this is the option. But again, we will try to evaluate what is this changeover point, right? And we'll also see, and for on, you can clearly see the slope should be 2 by 3. The slope is 2, so the option is B. But let's again try to evaluate at what point does this diode start to conduct. So as I told you that when when does the diode start to conduct? So we can draw the circuit like at that position as something like this, 2 volts, 2K, and we'll assume that this has started to conduct, right? So this is 0.7. That is the condition that we have, right? And we'll assume that minimal amount of current has just started flowing, so I is approximately equal to 0. That's what we are going to assume. Okay, so again, if you again, now since the current is 0, there will be no voltage drop over here. So you can clearly see V naught will be 0.7 volts, and thus you can clearly see that Vi plus 2, if you apply KVL over here, will be equal to V naught, and this will give me Vi equal to minus 2 plus 0.7, which is equal to minus 1.3 volts. So at when V in is minus 1.3 volts, that means that is when diode will switch from off to on, right? So we can write that this will turn on at minus 1.3 volts. So we'll assume that this voltage is minus 1.3 volts, and this makes sense, right? So yeah, so B will be the correct option for this question. This is very similar to the last question. There's nothing new, just this polarity had been reversed, and that's all. So any comments regarding this, or questions, doubts, please feel free to ask. I'll pause a bit. All right, let's move forward. Again, very similar problem. This time
Hello,
again.
sir.
Yeah, go ahead.
Sir, slide number 8, sir.
Slide number 8. Hold on. Yeah, we are on slide number 8.
Okay, sir. That I want to see.
I'll be uploading these. I'm recording these lectures, so I'll be uploading them to the YouTube channel. I should have mentioned
Okay,
that.
thank you, sir.
So you need not worry about noting down, and the notes will also be available to you.
Okay,
So
sir.
you can refer later, right? So again, the same problem, rather the same approach. So this will be our model again, where V on is 0.7 volts, and again let's do case 1 when Vd is greater than V on. So now you can see the polarity in this question is reversed. So this will be my VD and this is the diode D. So when VD is greater than V on, then how will the circuit look like? Circuit will look like something like this, 2K, and we replace it with a battery of 0.7 volts. And this will be the notation because P is at the towards the bottom. This is VI and this is our V out. Again, assuming a current I is flowing in this circuit, we'll apply KVL and write, so VI minus I times 1K. This will be minus 2 volts. This is 2 volts minus 2, then minus I times 2K. This will be plus 0.7 equal to 0. The value of this voltage source is 0.7 volts. If you try to rearrange the terms, it will be VI minus 1.3 over 3K, and then if you again try to find out the voltage V out, it will be so this will be minus, so this is 0, this will be minus 0.7. okay, so your V out will be so it will be V out minus 0.7. if I apply Ohm's law across this resistor, this will be I times 2K, right? So yeah, this will be minus 0.7. That's correct. So this will be plus, so if it will go to other side, it will become minus 0.7, and this will be the value of if I put the value of I, it will be 2 by 3 VI minus 1.3 minus 0.7. This will come out to be 2 by 3 VI. So again it will be minus 2.6 by 3, approximately 0.9. This will come out to be minus 1.6. This will be our expression 1. Just give me a second. All right. ठीक है, now we'll do the case 2. Case 2 is when VD is less than V on, and again I draw the circuit diagram. Now in this case the diode will not be conducting, so it will behave like an open circuit, and thus no current will flow in this circuit. I'll assume I equal to 0. This is V out, this is VO over here, sorry for that. So I can simply, if I write KVL along this line, I can simply write VI minus 2 equal to V out. This will give me V out equal to VI minus 2. This will be my second case, or the second expression. Right, let me reproduce these values over here. So V naught is 2 by 3 VI minus 1.6. This is for on. For off, it is V naught equal to VI minus 2. And again we can see, again we'll assume that if we apply a very large negative voltage, right, let's say minus 100 volts, right, not minus 100, let's say minus 10 volts. So what's going to happen is that the current will flow something like in this direction, right? So you can see that this diode will be turned on then, right? So yeah, so this diode will be turned on. So we can clearly see for negative biases, for large negative biases, diode is turned on, and we can see the slope should be 2 by 3. So the answer should be A or B. C or D cannot be an option. And for large positive voltages, so this diode will be reverse bias, and thus we should have off condition, and thus slope should be 1. So it's one of these options. But then you also need to figure out what is the turn on voltage. So how do we find out the turn on voltage? As I told you, we'll as we saw earlier, we take the case when the diode has just started to conduct, right? So it will look something like this. So when the diode has just started to conduct, this means the current flowing here, by the current will flow in this direction, or you can, for analysis you can take in opposite direction, but I is approximately equal to 0. Very small amount of current has just started to flow. So if you try to solve this, so there will be no voltage drop across this resistor. So we can see V out should come out to be minus 0.7 volts. And if I put it in this expression, so VI minus 2 equal to V naught, so this will give me VI should be equal to 2 V naught plus 2, so minus 0.7 plus 2, this should give me, at this Vin, the diode should start to conduct. So at Vin equal to plus 1.3 volts, or alternatively you can see at Vout equal to minus 0.7 volts, the diode should start to conduct. So you can see when Vin is positive, in among these two, this is Vin is positive here, so this voltage is 1.3, and Vout should be negative, so this is negative, so this is something minus 0.7. So you can see option A matches for the, based on the turn on condition. So that will be our option. This is again very similar question, just that we are talking the 4 different configurations, and this is just KVL and KCL. I'm just repeating the analysis over and over again. Now coming to the last problem in this set. Just give me a second, let me check the time. Okay, we have time. Okay. So this is the 4th problem in this set. Again, the polarity is reverse, and compared to previous question, just the voltage polarity, the voltage source polarity has been reversed. And as usual, I'll simply put, this is the model that we are using, ID versus VD. Again, V on equal to 0.7 volts, and as we did earlier, case 1, when VD is greater than V on. This is my VD. Now note that I'm always keeping the P side as the positive. That's to denote that this is the to denote the forward bias nature. When VD is positive, we can clearly see that diode is forward bias, and this is the diode D. So VD is greater than V on, and I'll draw the circuit. This is 1K, 2 volts, 2K, and this is how the battery, this is, if we replace it by battery, it will look something like this. This is 0.7 volts. We are taking the output over here, and this is the input that we are providing. Again, assuming, again, the last question I took the current flowing to be clockwise. It doesn't matter for the analysis, because the main thing, the important thing here is that you place the polarity of the diode. When you replace diode with a voltage source, that polarity has to be correct. Now this is a circuit you can apply for analysis. You can just apply current, you can assume current to be any direction. So in this, now let's assume the current is in this direction, right? So now what's going to happen is, or let's say for the sake of consistency, I'll keep the current direction same, otherwise it might get confusing. Let's keep the current direction to be same, that is this, clockwise. All right, so I'll write the expression for KVL. So Vi minus I times 1K. We are encountering negative polarity, so this will be plus 2, and then I times 2K, again a negative polarity, so plus 0.7 equal to 0. We rearrange the terms, we will get I equal to Vi plus 2.7, 2 and 0.7 will get added up over 3K, right? And if I again try to evaluate V naught, so this V naught will be nothing but V naught, this will be I times 2K, that is the voltage drop over here, minus 0.7. What? Just give me a second. Yeah, because this is 0, right? So this will come out to be minus 0.7 if I assume this to be 0, that is. So V naught minus 0.7, that is the voltage drop over this, and so if we rearrange, this is how it will come. I'll put the value of I over here, so it will be 2 by 3 Vi plus 2.7 minus 0.7, which will come out to be 2 by 3 Vi, so 0.9, 1.8 minus, so this will be plus 1.1. So this is the, when diode is turned on, this is the output voltage that we are getting. Okay, now let's do quickly the second case. Second case would be when Vd is less than V on. In this case, as we know, we'll replace the diode with a open circuit, because we are operating now in this regime. So let's replace it with an open circuit. this is the input side, this is the output side, and this is negative, right? So no current will flow because it's an open circuit, and if we apply KVL in this leg on the top, we can write VI, this is negative polarity, so we'll encounter plus 2 equal to V naught. So we'll say V naught equal to VI plus 2. This is our second expression for the off state. So for on state we have V naught equal to 2 by 3 VI, sorry, 1 second, 2 by 3 VI plus 1.1. So for on state we have V naught equal to 2 by 3 VI plus 1.1, while for off state we have V naught equal to VI plus 2 volts. Okay, again we'll just analyze, let's say we apply a very large negative bias to this. Okay, this means this is at higher potential, let's say plus 10 volts, and this is 0. So we can see some current, this has chances of becoming forward bias, and the current will start to flow. So we see when we put a large negative VI, right, this diode will start to conduct. So for large negative VI, the diode should conduct. This means this should be the equation for between V naught and VI, and we can see we should have a slope of 2 by 3. So for large negative values, we can see we should have a slope of 2 by 3, which is only in one option. So option A, C and D, all of the three get eliminated, and when VI is positive, let's say plus 10 volts, this diode is reverse bias, and you can see then this means off, and this means there will be a slope of 1 between V naught and VI. So this is supposed to be the slope over here. So option B is correct, but for the sake of completion, I'll find out the voltage at which the diode just starts to conduct. And as we know that we find it like this, we do it 0.7 volts, and we assume that the current, by the way, current will start, if we have to be technically correct, in this case we have to, because we are not analyzing, we are replacing it. So I will approximately be equal to 0, right? That's because the diode is just turning on. So if it's just turning on, this means there will be no voltage drop over here, and you can see V naught will come out to be minus 0.7 volts. And if you put V naught equal to minus 0.7 volts, and then we can see VI plus 2 equal to minus 0.7, this will give me VI equal to minus 2.7 volts, right? So that means at the point of switching, when the diode will turn on or off in this case, so VI should be minus 2.7 and V naught should be minus 0.7. This means V naught is negative, VI is negative. This is why X and Y both are negative. We must be in third quadrant. So this is the switching point. And if I want to write the value, so this will be this is the x-axis, so this is minus 0.7, and this is the y-axis, this is the x-intercept, this will be minus 2.7 volts. So you can see option B is the correct, and this is at this point is the diode is turning from on to off. In this case it's on for much negative voltages of VI, and are off for positive voltages of VI. The switching voltage is minus 2.7 volts, right? So I'll pause a bit over here because we have completed four problems which were similar in nature. I'll just summarize all four of them together. In this, what we had done was that for the given circuit, we just draw two circuits in which we broke into two parts when the diode is turned on and the diode is turned off, and accordingly we applied KVL and we solved the expression, and finally it was just a very simple matter of plotting them, which was very straightforward. And we also find out the switching point, that is, you can see, for in this case, in this problem it was minus 2.7 volts of Vn. So that's it for these first four problems. I'll again pause and wait for your comments if you have any doubts till now. Otherwise, if no, then we'll move forward. Since we have, I'll share my one second. So this is my email ID. If you have doubts, I mean, it's better if you post it on the discussion forum so that others can also benefit. But if for some reason you need to be specific that you want to ask me, you can send email on this. And the YouTube channel is also by the same name. So YouTube channel name is also the same, Learn with Amit Bansal. I'll be uploading this to the YouTube channel. So let me, so this
Hello,
is,
sir.
yeah, go ahead.
So the assignment which we get every week,
Uh-huh.
so that can we discuss with you?
No, I mean, the for instance, the assignment that is due, we cannot, I mean, if you have a specific, let's say, doubt uh, in some concept, right, you are more than welcome to discuss that. Yes, that can be addressed. But the specific problem, and especially the problem as a whole, cannot be discussed. If you have some, let's say you have some difficulty understanding some phrase in the problem, right, or there is something you feel wrong with the problem itself, you have tried it and you are finding some conceptual problem, or while solving or encountering some problem, that can be addressed, yes, but not the problem as a whole, or problems, in case you want more than one.
So then I will contact you in this email.
No, even then I will not, I can guide you for that's why I'm saying the idea is that we are not going to solve the problems. If you have some
Okay.
specific problem, you can write to me that, okay, that in this problem I did not understand this phrase, for instance, let me just get to this question. So this question talks about, in the circuit shown in the figure, vi is increased starting from 0 volts. At what value of vi will the diode turn on? Okay, so let's say, in this case, you are not able to understand the phrase vi is increased starting from 0 volts. That is, what is the relevance of this phrase, right? What do we mean by this phrase? That can be addressed either by email or in the class itself. But let's say if you want me to say, okay sir, let's please solve problem number, please provide me a solution to problem number 6 of the assignment, that unfortunately I'll not be able to do once the assignment has been submitted, right? For instance, I think the deadline for assignment 1 has been completed. I hope you have submitted that can be discussed, yes. So for the completed assignments, we can discuss in class or on email, whatever you may prefer.
Okay, sir.
Yeah.
Thank you, sir.
Yeah, all right. So now let's quickly jump to problem number 5. So this problem says that in the circuit shown in the figure, vi is increased starting from 0 volt. This means, so vi initially, this phrase means that vi initial at t equal to 0 was 0 volts, and increased means that we are increasing in the positive direction. So that means vi will start from 0, 0.1, 0.2 volts and so on, in the positive direction only. At what value of vi will the diode turn on? So you can simply see, when the vi is 0, there is no voltage source in this circuit, and this diode needs plus 0.7 to turn on. So this means nothing will be turned off originally at t equal to 0. So there will be no current flowing in this circuit. However, at some, so vi we have started increasing, let's say slowly. Now what will happen is that the current will start flowing in this circuit, right, over here first, because this is just a potential divider. Now what is the condition at which we are required to find vi at which the diode will turn on? So again, this is the problem that we require to find. So what I'm going to do is that we know that how will the circuit look like just at turn on, right? So I'm going to draw that circuit just at turn on. How will the circuit look like? We have discussed in the past 4 problems. So let me draw that circuit now. So this is vi R1, R2, and we know just at turn on, right, this will behave like a battery source, voltage source, right? This is R3. I'm writing this in words here. Just at turn on, there'll be 2 things. One, id will be approximately, we'll approximate it with 0 amps, and secondly, vd will approximate it with 0.7 volts. That's what I have already drawn a vd over here. So again, this is my vd, this is 0.7 volts, and I have assumed id will be approximately equal to 0. This means the current would have just started flowing through this diode and accordingly through this resistor. Okay, so now let's draw the currents. This will be, let's assume this is i1, this is I2, and let's assume this current to be I3. I3 will be, by the way, same as ID. Okay, so we know that this means now from this condition we can say that I3, which is equal to ID, should be equal to 0, because that is the turn on condition, right? So this is 0, correct? And let's label this voltage, right? Let's call this node A. So, and let's ground this node. Okay, so now if I apply, you can clearly see if this is 0, no voltage is getting dropped here. So I can clearly say VA minus 0 must be equal to 0.7 volts. This will give me VA equal to 0.7 volts. So I have obtained the voltage for this node. How did I obtain? Because there's no current flowing through that. You can either write KVL between A in this loop, right, or you can just write Ohm's law across this fellow over here, and it's the same thing essentially, right? So VA is 0.7 volts. Now what I can do is what should I do, right? So now I know yeah, the potential over here is 0.7, and I'm required to find VI also. So this is the first, this is the second concept. So I can write step 1, step 2, step 3. If I apply KCL at node A, what will this give me? Incoming current, which is I1, should be equal to outgoing current, which is I2 plus I3. Now I3 is 0. Yeah, is there some problem? Okay, I3 is 0, so this will give me I1 equal to I2. So I1 is equal to it. This means all the current that's coming through R1 will also flow through this same through R2. Now step 4, we write Ohm's law across R2. So this will give me I2 will be equal to VA minus 0 over R2, right? So this will, so VA is 0.7, R2 is nothing but 2K. This will give me 0.35 milliamps. I have obtained I2 now. Now I can simply find what is the value of VI by applying Ohm's law across R1. So that will be VI minus 0.7. This should be equal to I1 times R1, and this will give me VI equal to 0.7 plus I1 R1. The value of I1 will be the same as I2, which we obtained here, which is 0.35 milliamps. So I'm going to put this over here. So VI we obtained was 0.7 plus I1 R1, which is 0.35 milliamps, times R1, which is 1K. It will come out to be 0.7. Milli and K will get cancelled, and this will give me 1.05 volts, which is your option C. Yeah, so that's all in this problem. What did we do? We just simply, we know that at diode turn on, so this is the concept that we know, that the current through diode will barely be, the diode will just started to conduct. This means the current we can approximate it as 0, and the turn on voltage is 0.7 volts. So we replace this diode with these conditions, and we just apply some nodal analysis, Ohm's law, whatever you may want to call it, and we finally obtained that the turn on input voltage should be at 1.05 volts. So that completes our problem. I'll pause again for a bit here. If you have any doubts or comments, please speak. No? Okay, let's move forward. So second part of this problem asks us, in the circuit of question 5, what is V3 for Vi equal to 5 volts? Okay, so so then we first need to determine, for this problem we must first determine whether diode is turned on or not. So we in the last problem we saw that Vi for turn on was 1.05 volts, right? So now here the input is greater than that. So this means this diode would have turned on already at 1.05 volts. So we can see that, we can write, since Vi is greater than Vi turn on, which I'm writing this, D conducts. Right, now since D is conducting, so I can write thus equivalent diagram can be drawn as the diagram that I'll draw now like this. So this is 5 volts because we are given Vi equal to 5 volts. This will be 1K, this will be 2K, and now diode is turned on, so I'll replace it with a voltage source of 0.7 volts. This will be 2K, and I again assume this to be ground, and so this is, we are required to find V3, so this is the voltage that we are required to find. Right, so again what I'll do, simply I'll assume I1 is flowing over here, I2 flowing over here, and I3 flowing through the right loop. Okay, and again I'll assume the voltage here is VA. Okay, so there are different ways of doing it. For instance, what we can do, we can convert it, for instance, this left leg, right, 5 volts and 1K, I'll convert it to the Norton equivalent. So how will it come? It will simply be 5 over 1K, this will be 5 milliamps, and this will be 1K, 2K, and this will be sorry, this is 0.7, and then this is again 2K, right? And so 2K and 1K will be 2 times 1 by 2 by 2 plus 1, so that will become 2 by 3. So then I can again draw this as 5 milliamps, and this will come out to be 2 by 3K. Okay, and the rest of the circuit will remain same, 0.7 and 2K. Right, now again I'll simply convert it to the Thevenin equivalent. So these two terms will get multiplied to give me the Thevenin voltage, that is the voltage source again. This will be 2K by 3, this will be 0.7, this is the resistor of 2K, this is the voltage that we are required to find, and the voltage would be 10 by 3 volts because 5 times 2 by 3. Now what I can do is simply apply the KVL over here and assume the current flowing here is I3, right, this current I3 that I assumed earlier. So I can simply write KVL is 10 by 3 minus I times 2 by 3K, so there will be a drop of minus 0.7 minus I times 2K equal to 0, and I'll obtain I from here equal to, so 10 by 3 minus 0.7 divided by 2 by 3K plus 2K, so that's 6K, and so that will be 8 by 3K. Now what we required is to find V3, so this implies V3 is nothing but R3 times I3, so this will be 2K times, so 10 by 3 minus 0.7, so 10 by 3 minus 0.7, 10 by 3 minus 0.7 would be 2.63, so numerator is 2.63 divided by 8 by 3K, this gets cancelled, this will come out to be 3 times 2.63 by 4 volts. So this is coming out to be this is problem number 6, right? So this is coming out to be V3 is coming out to be 1.975 volts, 1.975 A. This is the closest option. If you round it off some things, I think, for instance, if you say 10 by 3 is 2.6 yeah, so 3.3 or something, you get some approximations, you will be fine, but we are close enough. So this is nothing but the extension of the previous problem. In this we just replaced diode by a voltage source because we are operating, because diode is already turned on, so we just replaced by this and solve the problem. Now the next question asks, In the circuit of question 5, what is the slope of V3 versus Vi at Vi equal to 5 volts? Okay, I think we have already solved this problem. Have we not? No, we have not, because we drew it like that. Okay, it's fine. So we are required to find this slope. So as what we did was that we found out this equivalent circuit for this, right? So I'll draw this equivalent circuit here again. So remember, this voltage came out to be 10 by 3, right? How did we get 10 by 3? It was Vi times 2 by 3. That's how we got it. And this was 2 by 3k, if you remember. And then this was 0.7. This was again R3, right? And this is the voltage V3. So what we have already derived this in the last problem itself. So I've just, because Vi was 5, this was coming out to be 10 by 3, and hence I am just replaced with the original value of Vi. Now what I'll do is then I'll again apply the KVL in this loop, right? Assuming current I is flowing, so this will give me the expression. I'll go to that expression again. So this was coming out to be, I was coming out to be 10 by 3 minus 0.7. So this is coming out to be, so 10 by 3 means Vi into 2 by 3 minus 0.7 divided by 8 by 3k, and this gave us V3 was I3, I times I3. So if I replace this value of I over here, this will give me 2k times 2 by 3 Vi minus 0.7 divided by 8 by 3k. So this is 3 by 4, 2 by 3 Vi minus 0.7. If I multiply this inside, this will be Vi by 2 minus 3 by 4 is 0.75. So 0.75 times 0.7, that comes out to be 0.525. So I have obtained that V3 is this expression. I'll again repeat, I have done nothing. We have already obtained this Thevenin equivalent in the last problem. Because Vi was 5, this is coming out to be 10 by 3. So I've just replaced it back in terms of a variable, and this is the expression that we are getting. So V3 equal to Vi by 2 minus 0.525, and this is by the way when Vi is greater than Vi on, which we obtained was 1.05 volts, right? So since 5 volts is greater than 1.05 volts, so we can apply this expression, and we can clearly see the slope is coming out to be 1 by 2. So D is the correct answer for this problem. Again, just building up on that, there's nothing new that I did. Just in case of the actual values of Vi of 5 volts, I just obtain the expression, and that is all, right? So if you have any doubts till now, please speak up. Otherwise we'll quickly move on to the next problem, because you have completed this set of 3 problems. Again, I'll just summarize the last 3 problems. In this, we were required to find when does the diode turn on, right? And we found that out by using, where did it go? Yeah, this theory. Just at turn on, ID would be 0 and VD would be 0.7, and we obtained the turn on voltage for VD, and correspondingly what will be the input voltage that is required. And then finally, once we had turned on, that is then we were operating at Vi equal to 5 volts, and then we found out what is the voltage for it, what is the output voltage, for instance, which we obtained over here. And then we found a general expression where we replace Vi, in place of 5 we placed Vi, and then we obtained this expression. Again, this is true when the device is turned on, because then only this circuit is valid. And then we found out that this was the expression, and the slope was 1 by 2. So any doubts, any comments? Otherwise we'll move on. All right, if no, there's a doubt? Somebody?
No, sir.
Okay, fine. So let's move on to the next problem. Now here, before we go on to this problem, this is the symbol that this is a diode that we typically know of, a PN diode, right? As I told you, like this is P semiconductor, this is N semiconductor, and this is the typical symbol of this diode. And as I told you, the characteristics of this diode, the IV characteristics, ID versus VD, if I draw the real world looks something like this, and at some point of time it just breaks down. So this is what we known as V breakdown, the breakdown voltage of a diode. And this is what, if we take a derivative of this, you can find something called V on, which we are assuming for silicon diodes to be 0.7 volts, right? So when you operate a diode in this region beyond breakdown, what happens is that this diode is no longer useful. So if the breakdown is avalanche type, this diode is no more useless. However, there are certain diodes based on doping, what we can do is that these can be reused. So you can see that what the advantage for this, if we operate over in this region, is that it can support large amounts of current, a few milliamps, tens of milliamps, and the voltage will not change. So this means that, and if the diode, and this in the forward, if the device is not burnt, then you can also use in the forward direction, but we need a special diode. Those diodes are called Zener diodes, and they're represented by this symbol, right? They're represented by this symbol, Zener diodes, right? So what they do is that when the reverse bias, if we reverse bias them beyond their breakdown, they will support large amounts of current. And the forward bias, they'll obviously behave like a normal diode. So this is the good point about Zener diodes. Hence they are also used in voltage regulation. That is one of their primary applications for Zener diodes, for voltage regulation, right? Now this is the theory part. Now let's apply this knowledge to this problem now. So what the question says, V on is 0.7 volts for both diodes, and Vz, by the way, this breakdown that I'm seeing is also sometimes referred to as Vz. So Vz is 3 volts. Usually breakdown for normal diodes is maybe 100 volts, 70 volts, 80 volts, or maybe 200, depending on how that was fabricated. But for Zener diodes, this voltage is very low. But in this case, you can see it's only 3 volts. Right, so this is a Zener diode D1, and its breakdown, or Zener voltage, as we see, is 3 volts. So we are required to find the slope of V out versus Vi when only D2 conducts, right? So when only D2 conducts, okay. So we can see that when D2 is conducting, right? So when D2 is conducting, this means, so let's call this as V2, okay. So this clearly means, so what I'll try to do is I'll try to replace this leg with the model that we have of our diode. So I can replace this. I can draw the circuit with something like this. So this is R1, this is Vi. We don't know what's happening to this leg. Let's forget about this for a minute, and let's draw this. So this will be 0.7 volts, and this will be 3.3k or R3. Right, but we also know that if now you can see if there is some current flowing over here, right, and it says that only D2 is conducting, D1 is not participating in this problem as of now. But we need to determine is that whether D1 is conducting in the reverse direction or not. That means, is D1 operating here or here? If D1 is operating in this region, this means there will be no current. But if it's operating here, it can drive some current, okay. So for now, we'll assume that there will be no current flowing through D1. So this is open circuited, right? So this means whatever current is flowing will flow like this, right? And this is the output voltage V0, which we are interested in finding out with respect to Vi. So it's a very simple problem. If I try to apply a KVL in this loop, so this will be Vi minus IR1 minus 0.7 minus IR3 equal to 0. I will come out to be Vi minus 0.7 over R1 plus R3, and thus I can write V0 should be equal to, that would be so this will be I times R3, and then we add a 0.7, so this will be 0.7 plus I, the value of I is this. I'll write this expression first. It will be 0.7 plus Vi minus 0.7 R3 over R1 plus R3. So let's put these values just to get the answer. So Vi is the variable, so we will not change that. So Vi minus 0.7 times the value of R3 is 3.3 over 5.1, right? 3.3 plus 1.8, so 3.3 over 5.1 comes out to be 0.65. So this will be 0.65 Vi minus, so this will be 0.65 and this is minus 1, so this will be plus of 0.35 into 0.7. This is coming out to be 0.25, right? So the expression is coming out to be, we have obtained that V out is coming out to be 0.65 Vi plus 0.25. Again, I have assumed that the D1 here is operating, is not in Zener diode regime yet. Okay, so so because this is the expression for yeah, this is the expression that we have obtained. So you can see that this will require it at a higher, at least 3 volts it will require for D1 to be start conducting when in its breakdown mode, right? But if you see, if you, let's say if I apply Vi of 2 volts, right, this will only be 0.65 times to 1.3, this will only be 1.55 volts, which will not be sufficient to support the Zener the Zener breakdown for this diode. So that means D1 is completely off, right? It's not operating in Zener mode or in the forward mode. So this is the expression that we have obtained, that's on your screen. And so we are required to find the slope. So we found the slope as 0.65 because this was the expression. I'll write this again here, 0.65 Vi and plus 0.25 volts. So you can see the slope is 0.65, right? So now now this problem, the second leg of this problem. Okay, do we have any doubts regarding this problem, problem 8? It was given that only D2 conducts, so D1 was, we completely eliminated from the picture, and we simply find out V out versus Vi by using KVL, and nothing else, nothing special, just that D2 has to be eliminated from the picture, right? Now we'll quickly move forward. Now it says that D2 is forward and D1 is reverse, right? So it's clearly say it's conducting in reverse direction. This means now we'll assume this to be in our Zener mode. Okay, so how will the circuit look like then? Let's draw this. So this is R1, this is Vi, this is conducting, right, in the reverse bias mode. Remember that. This means your N side now will be, N side will be like, behave like a positive terminal of the battery, and this is your R2, this is grounded. D1 is also D2 is also forwarded, so D2 is also contributing as 0.7, and this is your R3, this is grounded. Again, this is your V out, right? So the problem asks, again we are required to find the slope of V out versus Vi. So that means that, so let's assume the node voltage, okay, here is given V, let's call this node A. Okay, and let's assume the current that is flowing here is I2 and the current that is flowing here is I3, and this current is, so if you apply KCL at node A, right, so we can say that, so this is step 1, KCL at A, I can see incoming current I1 should be equal to I2 plus I3. So now we just need to evaluate what is the value of I2 and what is the value of I3. Now to do that, we can apply KVL along D1 path, that is KVL along this route. So if I write KVL, so that would be V naught, so this is a positive terminal that we are encountering, so V naught minus 3, right, minus I2 R2 should be equal to 0. So this will give us I2 equal to V naught minus 3 over R2. So this is the expression we have obtained for step 3. Again we will do KVL along D2 path, that is along this path, the right path. Again I'll write, I can say V naught, because this node voltage is V naught, minus 0.7 minus I3 R3 equal to 0. This will give me I3 equal to V0 minus 0.7 over R3. Now I have got I2 and I have got I3. Fourthly, we also need I1. So I can simply say Ohm's law along R1. If I do that, it will be Vi minus V0 equal to I1 times R1. So I1 will simply come out to be Vi minus V0 over R1. Now we know I2, this, and this. All these three values will put in this expression, the KCL that we had obtained. Okay. So I know I1 came out to be V0 minus V0 over R1. I2 came out to be V0 minus 3 over R2. And I3 came out to be V0 minus 0.7 over R3. Now let's quickly put the values of let's quickly put the values of resistances. This will come out to be Vi minus V0 over 1.8 equal to V0 minus 3 over R2 is 2.2k. K and so let's put K, but they will get cancelled. V0 minus 0.7 over R3 is 3.3k. So K's get cancelled, and I'll collect all the values of V0 to one side. I'm bringing them all to the left. Okay, this is coming out to be V0 1 over 1.8 plus 1 over 2.2 plus 1 over 3.3. all of them will come on the right side. Let's say this will be equal to Vi over 1.8, and this will be 3 by 2.2 plus 0.7 by 3.6. So this is the complete expression that we had obtained. Right now I'm solving this here, so this will come out V0 should be equal to, now remember we are only interested in the slope, right? So when this term goes over here, let me just solve this term over here itself, whatever we have in the the three terms that are in parallel, right? So that will be 1.8 times 2.2 by 4, right? That will come out to be the first term. So that's coming out to be 1. Yeah, so that's coming out to be 1. So now 1 is parallel in 3.3. So what I mean to say is, be more clear. So the first two terms, so this will be 2.2 plus 1.8, so that will be 4 divided by 1.8 by 2.2, so that's coming out to be 1. So that will be 1 by 3.3. This is Vi by 1.8. Let's solve the constant term also. 3 by 2.2 is 1.37, and 0.7 by 3.3 will come out to be 0.21. Okay, so now let's solve this term also now. So this will come out to be V0 times 4.3 by 3.3. This will come out to be Vi by 1.8 plus 1.58. Right, so then V0 will simply come out to be 4.3 by 3.3 will come out to be 1.3. So this is 1.3 V0 equal to Vi by 1.8 plus 1.58, and so V0 will come out to be 1.3 by 1.8. That's 1 second. Right, just give me a second. Yeah, so this is coming out to be so this will come out to be Vi 1.8 times 1.3 plus 1.58 by 1.3. So 1.8 times 1.3 and inverse of that coming out to be 0.43. So this is coming out to be 0.43 Vi, and the second term will come out to be the constant term, that is 1.22 volts. So this is the complete expression that we have obtained, and you can clearly see the slope is 0.43, which is the option over here, option A. So just to reiterate again, in this problem we were given that D2 conducts in forward direction, D1 conducts in reverse direction. And as I've already told you, that for Zener diode, because so D1 is operating somewhere, for D2 is operating somewhere here, okay, but D1 is operating in this problem over here. Hence both of them are conducting, and then we drew their equivalent circuits, we replaced them with the voltage sources, and then it's after just KCL and nothing, KCL, KVL and nothing. This is KCL and KVL, rest is just algebra, so that's nothing to worry about. So that's that. Any doubts, any comments regarding till now that we have, because we have 2 more legs to go in this problem. Right, okay, so now it asks, now it says us that D1 is forward. So as I told you, this diode can operate in both the regimes. The Zener breakdown, it will give it will some good a few milliamps, and always also in forward direction this can operate and give a few milliamps. So this is in forward. This means D1 is operating like a normal diode, like a normal PN diode that we are aware of, and D2 does not conduct, so D2 is shut off, right? Yeah, so D1 is forward and D2 is shut off. So this means the circuit now will look something like this. This will be a very simple circuit now. VI, so we know D1 is conducting in forward, right? So if D1 is forward, D1 forward means P side should be at the positive terminal, which is 0.7 here. This is R2 and this is grounded, and this is open circuited because this is given in the problem. This is R3 and this node was V0, right? So now I'll redraw this circuit because there's no point repeating this. So I'll simply write, I can draw this as VI R1, this is R2, and this is the V0 that we are required to obtain, right? This is the polarities that we can take, right? This is a very simple problem. I'll apply KVL over here, so I can write VI, let's assume the current to be I, VI minus I R1 plus 0.7, this is a voltage source of 0.7 volts, and then minus I R2 equal to 0. This will give me I equal to VI plus 0.7 divided by R1 plus R2, and thus I can get V0. So V0 we can write as we can write it in 2 ways. We can write in terms of VI and we can write it over in here terms also. So I'm going to write it from this side. So this will be minus 0.7, because if this this will be at I times R2, right, plus I times R2. So this will be at I R2, and then we'll drop 0.7 volts over here, right? So this minus 0.7 plus the value of I is this, the value of R2, now let's put 2.2, R1 plus R2 will be 4, right? So this will come out to be VI, the coefficient will come out, 2.2 by 4 is 0.55. This will come out to be 0.55 times VI plus, and so no, this will be a negative, 1.8 by 4. This will be 1.8 by 4 times 0.7, that is 0.315. So we obtained V0 equal to 0.55 VI minus 0.305, V0 equal to 0.55 VI minus 0.315. This slope is 0.55, which will give us the option C as the answer, right? Again, very simple straightforward problem. D1 was conducting in forward, D2 is not conducting. We just draw the corresponding circuit diagram. We open circuited D2 and we placed a 0.7 volts battery source for this, and we obtained the expression like this. Now coming to the last problem, now we are required to find, this is interesting, what is VI for which D1 starts conducting in the reverse direction, right? So what I'm going to do, So we are considered only with D1 first of all. Okay, so this is like this. This is ID and VD. D1 starts conducting in reverse direction. Okay, this means we want to be operating over here, right? This is what we are interested in finding out, this voltage, this specific voltage, and we know that this specific voltage, which is Vz in this problem, is given to be 3 volts. By the way, this is magnitude of Vz because it's a negative side, so it will be actually -3. Here also this is the modulus, right, of 3 volts. So we know Zener voltage is 3 volts. So what will happen is that, so I can simply say, so when D1 starts conducting, there will be two things. Because it has just started conducting, I can say I will be approximately equal to 0, and second, Vz or Vd, which you can say, will be equal to magnitude of Vz, which will be equal to 3 volts. So these are the two conditions that we are required to follow, and we'll be fine with that, right? And we are required to find the corresponding Vi when this condition is satisfied, right? So let's do that now. So what I'll do is, first of all draw the equivalent circuit diagram that we'll see. This is R1, this is Vi, and this will be replaced by a +3 volts, right? And this is R2, this is grounded, this will be 0.7, and this is R3, this is V0, right? So when this has just started to conduct, this means I can assume that the current over here, as I told you, will approximately be equal to 0. This means this voltage over here, V0, now I can write, since I2 is approximately equal to 0, what I can say is that V out will be equal to 3 volts, because it's 0 here, and so that potential would be 3 volts. So V0 is, if V0 is 3 volts and there is some current that will be going through here, that is I3. So this is our step 1. Step 2 would be, we find what is I3. So I3 would be nothing but V0 minus 0.7 divided by R3. So that will be 3 minus 0.7 over 3.3. So that's 2.3 over 3.3. That will come out to be 0.7 milliamps. This is 3.3 K. So I3 we have obtained now. So what will be I1 now? For step 3, we'll apply KCL at node A. KCL at A will give I1 equal to 0 plus I3 node. This is I2, which is 0. This means I1 is coming out again to be 0.7 milliamps, and thus finally step 4, if we apply Ohm's law across R1, so I can write Vi minus V0 equal to I1 R1, and this will give me Vi equal to V0 plus I1 R1, and let's put all these values over here. So Vi, the value of V0 we obtained was 3, plus I1 was 0.7 milliamps times 1.8 K. This will come out to be, so 1.8 times 0.7, this is 1.26. The answer should be 4.26 volts, 4.25 volts. Okay, yeah, so that is the answer that we had obtained. So 1 2 3 4 5 6 7 8 9 10 11, yeah, so we have obtained this answer. So just to quickly reiterate what we have done over here is that we are required when D1 starts conducting the reverse direction. Okay, so when D1 starts conducting the reverse direction, this means that this has just turned on, so there will be no current flowing through here. But so we obtained the value of V0, that we have that what value of V0 will be encounter, and corresponding then we find out I3 and then I1, and then finally we apply the Ohm's law over here, and then we simply obtained the value of Vi. So that is the answer. So 4.25 or 4.26 volts is what we have obtained. So that's that. Now I'll again pause. If you have any doubts or comments, please feel free to ask. Just give me a second. अभी क्लास चल रही है, ठीक है मैं आता हूँ थोड़ी देर. Yeah, sorry. Any doubts or comments, or we can move forward?
One,
Yeah, go ahead.
if in forward direction it is conducting, what is the use of reverse direction conducting?
No, it's not. So as I told you, where was that? Yeah, so what? No, not here. Yeah, here. So what happens is that usually diodes, we assume that they conduct only in one direction, which is true for most of the p-n junction diodes. They conduct only in forward direction. In reverse direction, if you apply a very high voltage, they break down and the diode is just useless. It will not work properly in the forward direction. However, sometimes we want to regulate the voltage. Let's say we want this voltage to be fixed, we do not want to move it to a certain extent, right? For instance, in some application, let's say you want your voltage to not be varying by, let's say, you want it to be varying between 4.8 to 5.2 volts. In that case, you'll design such a circuit, and if you use Zener diodes, so what they'll do, when they'll conduct in reverse direction, they'll fix their voltage. They can support any amount of current in reverse direction, huge amount of current, but the voltage dropped across them will be fixed at 0.3 volts, in this case 3 volts. So that's the advantage, when we, even in reverse direction, that we can use. Typically they are not used, p-n junction diodes, yes, but for Zener diodes are used for voltage regulation purposes. That's the point I was trying to make. The utility in reverse bias, that's their utility in the reverse bias. Does that answer your question?
So the current, how much it can withstand?
That's so. Usually, every electronic device will have a rating associated with that. Usually, a power rating or a current rating that it can only withstand, let's say, 100 milliamps, 1 amps, whatever. This question I'll be better able to answer when we come on to the last problem. Okay, there we'll see the same thing. I just request your patience till then. All right.
Yeah, okay, yeah, sure.
Yeah. Thank you. So we have 12, 13, 14, and 15. Yeah. 1 second. Where were we? Yeah, okay. So what I'll do is that, let's first answer that question, okay, which you had just asked me. So what I'm going to do, I'm going to do 14 and 15 first, and then we'll come back for 12 and 13, right? Because Zener diode, it's better if you do it this continuation. So in this case, it says a simple voltage regulator circuit is shown. This is what I was telling you, that a Zener diode works as a voltage regulator, and we'll see how. To ensure proper operation, Zener diode, which has Vz equal to 10 volts, so this is given for this diode, Vz equal to 10 volts, requires a minimum of 10 milliamps. So as I was telling you, right, so this is given as 10 volts, the modulus of it, and it requires at least 10 milliamps. Okay, so that is one thing, 10 milliamps it must require. Also, so I can say that, let's call this T. So ID must be greater than equal to 10 milliamps, right? And it also says the maximum power dissipation is 1 watts. This means Vz times ID must be less than equal to 1 watts. This is what it says, and this is, we are talking in reverse direction. So now you're asking what is the maximum current it can support. So if I put Vz equal to 10 volts, which is given, so 10 times ID should be less than equal to 1 watts. This means ID should be less than equal to 100 milliamps. Okay, and we know ID should be less than equal to 10 milliamps. So this means for this Zener diode to work effectively at, for Vz equal to 10 volts, ID, this is the condition. Does that answer your question now, what you were asking me?
Yeah, exactly. I got the answer.
Yeah, thank you. So now the questions are, the input voltage can vary from 12 to 15. So this Vi is not constant. So this is varying from 12 to 15 volts. What is the minimum value of R that is required? So we are required to find the minimum value of R. Okay, so this is the problem. This is all that is given to us. Okay, we are required to find R minimum. This is the diode D. So what I'll do first of all is I'll replace this. Okay, I'll replace this with I'll replace diode with the known components that. So since this is reverse bias, so this will behave something like this. N will become the positive terminal, will behave the battery's positive terminal. This is RL and this is like this. Okay, this is your 3 volts. Okay, so now what is required, what is the value of R minimum? So what I'll try to do is that, so let's assume this node to be V0, right? And let's apply, yeah, okay, so you can clearly see that V0 is 3 volts. So this circuit you can clearly see V0 equal to 3 volts. And so let's assume this current is IL, and let's assume this current is I, and the current flowing over here is ID. Okay, so this is the first piece of information that we have. Now using this, I can simply say IL is equal to V0 over RL. So V0 is 3 times 1.5k. So this is coming out to be over, oh sorry, I made a mistake, my bad. This is not 3 volts, this is 10 volts. 3 volts was in previous problem. So this is 10 volts. So this is 10 over 1.5. So this will come out to be 6.67 milliamps. Very good. So now what I can see is that now let's try to find out I. So I can write I is equal to Vi minus V0 over R, right? This is, let's call this expression 1, this is expression 2. And if I apply KCL at node V0, at this node at V0, incoming current is I, this should be equal to outgoing current, which is ID plus IL. This will give me ID equal to I minus IL. Now we know that I minus IL, right? ID is if you remember, we had obtained ID should be greater than equal to 10 and less than equal to 100. This is the expression that we had obtained in the last slide, right? Now what I am going to do, I am going to plug in all the values that we know over in this expression, right? So let's do that. So I'll get 10 less than equal to, the value of I is Vi minus V0 by R. So that's Vi minus 10 by R minus IL. So IL I obtained was 6.67. So everything is in milliamps. Just please note that, less than equal to 100. So this will give me 16.67 less than equal to Vi minus 10 over R less than equal to 106.67. Nothing, I just taken 6.67 to the other side, nothing else. Okay, so this will give me, now what I'm going to do is I'm going to flip the sign of it. I'll take inverse of everything. So this will give me 1 over 16.67. The units is milli, so please note that milli should be greater than equal to R over Vi minus 10 should be greater than equal to 1 over 106.67 milli, right? This is also milli. So this, what this will give me is that this will give me 1000 over 16.67. So that comes out to be 60. 60 should be greater than equal to R over Vi minus 10 should be greater than equal to so this is the expression that I have obtained now. Okay, we are required to find the minimum value of R. So this means we only take the right hand side. So drop left side. So what will I get? I'll get R greater than equal to Vi minus 10 times 9.37. Okay, now Vi I know ranges from 12 to 15. Okay, so we want this circuit to work for every voltage of Vi, right? So for that we need to put Vi equal to 15. So this will give me R greater than equal to 5 times 9 point, because 15 minus 10. Okay, I'll do that. I'll write that for what I mean is that circuit must work for 12 volts less than Vi less than 15 volts, right? So this would mean that R should be greater than equal to 15 minus 10 times 9.37. This will give me R should be greater than equal to 9.37 times 5, which is 46.87 ohms, and which is the option A over here. So this is the problem. Why I took, so even if you put 12, let's say you want to put 12, so 12 minus 10 will be 2. 2 times 9 point something would be 18.75. So for case of 12, you will get R should be greater than equal to 18 point something. And for 15, you are getting R should be greater than equal to 46.87. You take their intersection, and so that will be R greater than 46.87. However you may want to look, I just took it like from, rather than going to the set theory, I just made sure that for extremes it should satisfy, and that is it satisfying. So R should be greater than 47, and then we will be good. So that is the thing over here. All right, so here we have calculated the minimum value of R, right? Now second part asks what is the maximum value of R. So again, remember that we had obtained this expression, right? 60 greater than equal to R over Vi minus 10 greater than equal to 106 point, greater than equal to 9.37, greater than equal to 9.37. Now we want to find R max. This means we'll use this inequality. So what we'll get is R less than equal to 60 times Vi minus 10. So again you can take two cases, right? When Vi equal to 12 volts, what will happen? This will give me R less than equal to 60 into 2. So this should be 120 ohms. For Vi equal to 15 volts, this will give me R less than equal to 60 times 5, 300 ohms. Now since the circuit should work for every condition, so what's the common between them? R less than 120 and R less than 300. We can clearly see that the common between them should be R less than equal to 120 ohms, and hence the answer would come out to be D. So this is just a very closely related problem to the previous one. But just to summarize what we had done, that Zener is operating as a voltage regulator, and this means this must always be in the reverse bias direction, and hence we draw this circuit. And since there were a very simple problem, we must find out, this was the main thing, apply the KCL, and then we know that ID should be, this is the expression that we had obtained, that ID should be between 10 and 100 milliamps, and we will put this inequality here, and the rest is algebra. So very straightforward problem. So I'll again pause a bit over here. If you have any doubts, please go ahead. All right, let's quickly come to the final two problems we are learning. Any doubts?
So in forward bias, can't we use it as a voltage regulator, right?
No, we cannot. I'll tell you. Okay, so I understand why you're saying that. I can sense. You're saying that since this, I mean, qualitatively, this part of the curve and this part of the curve is the same, right? That's what you are arguing?
Yes, yes.
So yes, again, there are few things that we have assumed over here. See, here it will, the current will continue, here the current will also rise. That's so that, but in our model, if I told you that on the right side it rises exponentially, right, with Vd. So even though we are saying that in all our models we have assumed that R on is equal to 0, because we have drawn it to be a vertical line, which is not the case actually. In reality, there is slope over here, so that R1 comes into the picture. So when you say voltage regulator, so for instance we are talking about, let's say when we say that it's 10 volts, right? If there is an internal resistance also, right, so there will be some voltage would be dropping. However, when you operate in reverse bias, right, that internal voltage is very small. It's orders of magnitude smaller than your forward internal resistance. So by looking at the graph, it may seem to you that the first quadrant, third quadrant are equivalent. Yes, in this model they look equivalent, but there is ideally there is not ideally, in reality there is a slope associated with that, with this, which is much larger than the slope associated with this. Hence it's better to use in this configuration. Okay.
Thank you very much.
Yeah. So let's now quickly come to this. Right. Okay. So the question says an input voltage Vi equal to V1 plus Vm sine omega t. So let's quickly draw this. How does it actually look like? Right. So this is Vi and this is time. So at time equal to 0, the voltage is V1, that is 3, and then superimposed on that is a sinusoid of 4 volts. So this goes something like this. So this would be 7 volts, this is 3 volts, and this is minus 1 volts. Okay. V on is 0.7 volts, so this that's given to us, and finally we need to find the voltage V naught. All right. So if you refer to the lectures of Professor Patil, you will see that this is the circuit of a peak detector. Okay, this is the circuit of a peak detector. I'll just quickly just tell you what's going to happen. So you can see at time equal to 0, if the capacitor is uncharged, right? So first of all, let's say that this is a peak detector circuit. Okay, so peak detector circuits usually have the constant voltage as time approaches infinity, right? So so what's going to happen is that so at time t equal to 0, this capacitor is uncharged. So if you can see, and at time t equal to 0, we are also given that this Vi is, if you remember, this Vi was plus 3 volts, like this. This is Vi. This is our Vi with respect to time. So this was plus 3 volts. This will be plus 7, and this is plus 3, and this is minus 1. So if Vi is plus 3 volts, you can clearly see that this diode is reverse bias. So this this diode is reverse bias, since Vi, since its positive terminal, its negative terminal is connected to plus 3 volts and positive terminal is connected to 0 volts. So this diode is reverse bias. So there'll be nothing happening in this circuit, right? So when will things start to happen? As always, we know that when so we need to know when will this diode start, when this diode start conducting. This is obvious when this Vi will go less than 0, somewhat less than 0, and then only somewhat sometime after that it will start to conduct. So let's first find out that time when D starts conducting, right? So let's try to find out that time. So when D starts to conduct, we know that we'll replace it with the voltage source, right? And this is Vc, and this is your Vi. This is V naught. So we know that this voltage will be 0 because we are starting just starts conducting. So we'll say just starts conducting, and we know that Vc is 0 because there's nothing to charge this capacitor, right? So Vc equal to 0, and since it just started, so we can also say that I is very close to 0 because it just started, right? So you can clearly see that will happen if we apply KVL. This is 0.7. So you can clearly see that will happen when Vi will become equal to, so you can see you can say Vi plus 0.7 equal to 0. This means Vi equal to minus 0.7 volts. So when Vi becomes minus 0.7 volts, right, then only the current will start to flow in this circuit, right? Okay, so let's say the current starts to flow after Vi crosses. So diode conducts when Vi is less than equal to minus 0.7 volts. So minus 0.7 volts would be somewhere over here. So I'm drawing it in a different color. I'm drawing it in the purple color. So it will start conducting only after this time. So it will not conduct up until here. Right. Coming back. Now when it starts to conduct, this means now this capacitor will keep on charging. And we have, since we have assumed that since R on is approximately equal to 0, this means tau RC, which is R on times C, this will approximately be also 0. This means this capacitor will get charged instantaneously. This means whatever is the output voltage, it will quickly get reflected over here. So let's try to find out what is the output voltage for this when Vi starts to conduct, right? So this is when Vi now less than equal to minus 0.7 volts. So again, if you apply, so there will be some current flowing. So we can clearly see that Vi will be V0 will be Vi minus 0.7 volts. Sorry, Vi plus 0.7 volts. If I apply KVL over here, that will be Vi plus 0.7 minus V0 equal to 0, and you will get V0 equal to Vi plus 0.7. So we have obtained that V0 equal to Vi plus 0.7 volts, right? And note that capacitor can never get discharged. Capacitor will only get charged because for capacitor to get discharged, diode will have to conduct in reverse direction, and this is not a Zener diode, this is a normal diode. So capacitor, whatever charge capacitor has accumulated, it will never get discharged, right? So this means that V0 is Vi plus 0.7 volts. So we have obtained V0 equal to Vi plus 0.7 volts, and mind you, this is for Vi less than equal to 0.7 volts, minus 0.7 volts, sorry. All right. So we can again I'll draw the diagram over here for Vi. I'm only drawing one cycle now. Okay, so this is 7, this is 3. Just give me a second, draw proper diagram. So this is 7, this is 3, this is minus 1, right? And we just figured out that it will start conducting only after it crosses it's less than 0.7. This means it will only conduct during this regime, or maybe even up to here, right? So what's going to happen is that now I'm going to draw how will the V output look like. So we know V output is 0 earlier, right? And we know nothing is happening until this time, so V out will remain 0. And we know after that we calculated this is Vi plus 0.7 volts provided Vi is less than equal to minus 0.7 volts. So this means in this regime V out will also start to change, right? And V out will follow, if we add will follow Vi, but just a lag of 0.7 volts. So if we so if the value of Vi is 0.7 over here, this means V out will be 0. And if Vi maximum is minus 1, so I'll put that V0 max can be minus 1 plus 0.7. This is coming out to be minus 0.3 volts. So it will go to minus 0.3 volts, just like following a sinusoidal, and then it will stay constant. Why? Because beyond this point, right, diode will become reverse biased. Diode will become reverse biased, and thus diode can never conduct. So this means this will now go to this value is 0.3 volts, minus 0.3 volts, and it will stay at this till infinity. Hence our answer would be option D. The more theory of it you can see in the lectures, but this is I told you this is called the peak detector circuit, right? So what I did in that is that I just found out when does this D start conducting, and we noticed that this capacitor will never get whatever charge it accumulates, because the current never flow in the opposite direction in this. So this capacitor, whatever charge it accumulates, the negative charge in this case, it will never get discharged, and which we'll see in this waveform. So you can see it accumulates a charge equivalent of minus 0.3 volts. It will never get discharged because diode will never conduct in the opposite direction. And this is called a peak detector circuit. Now coming to the final problem. So this is a circuit diagram that is given. So these circuits are also known as clamper circuits. clamper circuit. So again, this is the same waveform as the previous problem, V1 plus Vm sine omega t. V on is 0.7. We are required to find the voltage V out, right? So again, what I'll do is that first I'll assume that the diode is conducting, okay, and we'll try to see that how does it follow the input waveform. So first what I'll do is I'll draw the input waveform. I'm drawing only one cycle for the sake of simplicity. So this is Vi and this is T. This is 3 volts, this is -1 volts, and this is 7 volts. Okay, so let's assume when Vi is positive, it starts from 3. So this means now that, and Vc is initially 0. So Vc is 0 at t equal to 0 second. We assume the capacitor is uncharged initially. So so when it starts, so a current will start to flow. So what will happen is that this capacitor will get charged to a certain extent, and again we'll assume that since the internal resistance of diode is 0, so charging will be instantaneous, right? So tau RC would be 0. This means instant charging. Right. So now if I draw V out, that is what we are required, right? Yes, V out. So let's say when the diode is conducting, so what will happen is that, so V out, you can clearly see is that V out for the first cycle will be nothing but the 0.7 volts, right? So what will happen is that V out will continue when the in the first cycle, when the diode has turned on, and the capacitor will also charge. So what will happen is that V out will come out to be 0.7, right? And what's going to happen after this? So this is V out, so this value is 0.7, right? Then what will happen is that after a certain point of time, somewhere over here, this diode will get reverse biased, right? And this will be turned off. Okay, this is turned off. Then what's going to happen is that then no current will flow, and hence this voltage will output voltage will follow whatever the input voltage is. You can see that if this is turned off, then what's going to happen is that V out will follow whatever the V in is, right? We can, if I can write KVL over here, this will be, and let's say the charge is something like this. So Vi minus Vc equal to V naught, right? And you can see V minus Vc, right? So so output voltage will keep on simply following the input voltage minus the component of Vc, and the capacitor can maximum be charged to this potential, whatever this diode voltage is. So what's going to happen is, so what's eventually going to happen is, where was the problem? Wait. Okay, sorry. Yeah, so what's going to happen is that this will simply follow whatever this circuit is, whatever the input is doing, right? So whatever the input is doing, it will simply follow that. So it will simply be following, like after this, for this circuit, like this, it will simply be following whatever the input circuit is, because this is only shifted by a VC, and hence this is called as the clamper circuit. We are running out of time, so I'll not take more of your time, but for more details, I'll again visit this problem again in the next class. Unfortunately we have run out of time, but for more clarity, you can see this problem directly is explained in the lecture by Professor Patel also. So that's that. So that's it from my side for today. I'll stay back if you have any doubts or comments or questions. So thank you for staying late.
Thank you.
Geeta, Javed, if you have any doubts, you can ask.
Hello, sir.
Yeah.
Sir, can I ask you a question out of the topic?
Yes.
If your permission is there.
No, yeah, you have, feel free to ask.
Sir, it is my first class, if I say truly.
Okay, okay.
So whatever you have said, it was I have understand, but some topics it
Uh-huh.
was
Uh-huh.
you can understand, sir.
Yeah.
So I think the course started from 23rd January.
Yes.
So at that time our first semester was going on, sir.
Okay.
So today I have login and some of the previous assignment I have also missed because that have also gone.
Mm-hmm.
So, sir, what can I do now, sir?
So what I'll suggest you to do is just go through the for instance, I think week 4 lectures are also live, if I'm not mistaken. Whichever lectures are
Week
live,
four and five.
5 is also
Week
live.
four and
Okay, so naturally you'll start from week 1. Okay, the start from week 1, go through the lectures. So as I told you, first week um, is Thevenin and Norton equivalence. Okay, which is, if you are, what's your background, if I may ask?
I'm electronics and communication
Which year?
engineering. First year. Now from Monday our second semester will start.
Okay, so I'm not sure. ठीक है, since you are electronics and communication, but you must have in your 11th 12th standard, you must have read about KVL and KCL, right?
Yes, sir.
So based on KVL and KCL, we have Thevenin Norton equivalence. Okay, so
Yes, sir.
that part, I think the first week lectures should be fairly simple to understand. And phasors is also there, which is nothing but your complex analysis. So that also should not be much of a problem. So my suggestion is go through the week 1 lectures. Okay, attempt the assignment. I know the solutions, I don't know whether solutions have been uploaded or not, but still you cannot submit the assignment, but still attempt it, try to solve it. Okay,
Yes, sir.
because and then week 2 is nothing but transients, that is RC circuit and RL circuit. Okay, that is again that's more or less based on your senior secondary physics, I should say. Okay, the electronics part
Okay.
is there. So RC circuits, we see tau equal to RC, and similarly for inductor circuits. Those also will be, you obviously will have to give time, but it's doable. That's what I mean to say, since you have it lagging behind. And week 3, which we did today, was diodes. I am not certain, they are introduced in, have you read diodes in 11th and 12th standard?
No, sir.
Okay, so, and I assume in the first semester also, they would not have talked about diodes much.
No, sir. There was a basic electrical engineering,
So
not related with electronics.
okay, so in electrical, it's unlikely that they talk about diodes. ठीक है, so you, because this course assumes some prerequisites, that you know what diodes are, and in the next class, in the next assignment, for instance, will be on rectifier, so that will be one more application of diodes. So it might be, to be honest, it might be a bit troublesome for you, because you'll also have a semester going on, because this will assume that you have some diodes of knowledge of diodes, and later some BJTs maybe. Okay, and amplifiers. So this assumes some prerequisites. So it might become a bit hectic for you, to be honest, because you're still in second semester, and diodes and
Yes, sir.
BJTs will be quite difficult to comprehend if you have not read it for the first time, because you're talking about directly applications here. For instance, when I wrote the diode equation, which is exponential IS exponential VD over KT minus 1, have you read that before, for instance?
No, sir.
हाँ
This no.
हाँ So that is based on semiconductor physics. We derive that expression in a diode, in a course which is on electronics, or semiconductor physics or semiconductor devices. We derive that expression in maybe second year or third year, you will see that. So in that sense, many of the things will, since you have not read it yet, so you will not be able to comprehend in thoroughly, I should say. But as far as circuit analysis part is concerned, that thing you can do easily, because that is nothing, that is just KVL and KCL. So that part should be
Yes,
fine.
sir.
But diode onwards, it should, I mean, it might cause a bit of problem. Just give me a second, I'll just go through the what syllabus is there after this. Okay, so week 3 was diode, week 4 is also diodes, 5 is BJT, 6 is op amp, 7 is op amp, 8 is op amp, and 9 is applications of op amp. Then you have digital electronics. JK flip-flop, T flip-flop, digital to analog converters, and so on. Since we have not read it and we assume a lot of things in that, so especially for the latter part of the course, it might create some how should I say this, it will be difficult for you, because you also have a semester going on, right? Second semester, as you told me, right?
No, first semester was going on.
No, now second
So
semester is going on,
it is
right?
completed now.
Now second semester will
Yeah,
start,
now
right?
I have stepped to second semester. It is started.
It
It is
started.
started just here.
Yeah. So since it has started, and this course, since you're not read on BJTs and operational amplifiers and their applications, so this will be quite involved, because you have not read those topics. It's not as if these topics are difficult in themselves, but since you do not have a base, and then second semester, I don't think you will be talking about BJTs and amplifiers in any of your, if I remember, at least I did not encounter any such in-depth topics in my second semester, or even in my second year for that matter. So you may want to see whether you want to what extent do you want to continue with the course, to be honest. I'm being very frank with you, because this assumes certain prerequisites. When you joined the course, did you see that how much what is the prerequisites and whatnot?
Means what are the structures of the course?
Structure of the course, and plus so for instance, I don't think it talked about see, if you go to the introduction page of this, it says that, I'll share my hold on a second, I'll share my screen, give me a second. Can you see the can you see a web page?
Yes, sir.
So you see this
Yes, sir.
prerequisites, right? So the prerequisite for this course is a basic
Basic
course in
course.
electrical engineering, KCL, KVL, network theorem, CC analysis. So in this, in when you talk about KCL and
So
KVL,
KCL and KVL I have studied, sir. KCL and KVL.
that's what I'm saying, that for the first 2 or 3 lectures you'll not face much problem. It's just you need to give time and you'll be fine. But for the latter parts, okay, especially when we talk about BJTs, now this is diode, you may be able to comprehend, but the intricacies of the circuits and BJT, and then when you go to amplifiers, operational amplifiers, then it will become much more involved, and you require a base for that. You can continue with the course anyways, it's not but my only concern is that since you will be busy with your seconds or your courses in your college, and plus this is a slightly higher level course. It's not a first year course, to be honest. We require some background in this.
Yes, sir.
So you are welcome to stay, you can watch the lectures and you can learn. You can join the doubt solving sessions, and you can go to the videos of go through the weekly videos that are uploaded or that are open for students. So for instance, as I told you, right, so week 4 is diode rectifiers. A week you will also see BJTs, bipolar. Have you read bipolar junction transistors? I think not, right? I don't think it's
Yes,
talked
sir.
it's not talked about in senior secondary physics. So that's
Yes,
what
sir.
I
You're right,
mean.
sir.
So here we'll be talking. The professor might go through a bit of a theory, but to appreciate it, it would be you'll not be able to comprehend much of it. That's what I mean to say. So that call you have to take, that how you want to do it, because to understand BJTs
Okay.
you need diodes. So theory will be talked about, that's not the case, but many of the things, it's better you pause for this course. That would be my suggestion, to be honest.
Okay, sir.
And maybe
Sir, in this exam,
uh-huh. Yeah, go ahead.
this if in exam it will be of MCQ base, or we have to write.
That I don't that I think will be communicated, or you can ask in the discussion forum. That's better.
Okay.
Just drop a question in the discussion forum, that how is it, because if I remember, just give me a second, usually there is something like it's declared here, that how is it going to be working. Okay, this is I've opened a slightly older page. If you open the current page, maybe they'll be talking about that. But if it's not clear on the web page, you can drop an email in the discussion forum. You know the discussion forum, right?
Yes, sir.
So just drop an email in that what is the exam, but how will be evaluated. Just ask like that.
Thank you, sir.
Yeah, you're welcome.
Thank you.
Yeah, thank you.